Okay, so what I want to do this time is to take a kind of quite ambitious deep dive into some of the amazing things that we can do using synthetic differential geometry. You see, there are certain ideas, particularly the ideas of forming map spaces and using infinitesimals, which can allow us to really do some very interesting things with synthetic differential geometry. So I'm talking about thinking about vector fields, thinking about flows, thinking about differential equations. I'm talking about how we can set up a model of integration. I'm talking about how we can think about laws of motion and physics, and how we can generalize lots of fascinating concepts to do with motion and physics. Now, I know I'm in the early stages in this course of introducing the different ideas, but I just think that some of these concepts, particularly things that we can do with map spaces or exponential objects, are so amazing that the best thing I can do is to try and reveal these kind of concepts to you early on, because I think it's going to help to motivate learning this kind of theory in a more methodical way when one sees how powerful the underlying concepts are. So that's the kind of format of this video. Okay, so this time I want to introduce what I consider to be really the most powerful kind of ideas in this synthetic differential geometry. And those are really what we might call exponential objects, or spaces of maps. I mean, there are many approaches towards continuous mathematics, but this particular approach is kind of specially designed so that we have certain kinds of structures, which we could call exponential objects or map spaces. And basically, this means that we can think about, say, all of the kind of functions or maps from one space to another as forming a space itself. And there are all sorts of consequences of the details of how this works, which makes it so much easier for us to think about so many different things that are going on in continuous mathematics. For example, ideas like tangent vectors, tangent spaces, vector fields, differentiation, integration. All of these kind of concepts can be put on a much firmer footing and made into something that's kind of easier for us to kind of get our hands on. So we're going to get to this kind of idea. Now, just to kind of introduce this, I want to remind you of a few things. So firstly, we have this smooth line, which we normally denote as R, and we might be talking about a particular point on this smooth line. So for example, we could write 7 is in R. Now we can think of this as the very simple statement that 7 is a real number if we were thinking about what this means in terms of regular mathematics. This is the sort of, this is the way of thinking about it that we often prefer, which is to say that 7 is a point of R, or if you like, we have this space here, which we denote as 1, which we can think of as just being a single point. And what we're saying is that there's a function which sends this single element in this space 1 to this point 7 here. And we can call this map 7 itself. So I was talking about this last time, this idea that we can think of points of spaces as arrows from this kind of space which we call 1. So now let's get on to talking about exponential objects or map spaces. So if we have a space A and a space B, then if we write A to the power of B, what this is it's the, we can think of it as a space of maps or functions, whatever you want to call them, from B to A. Okay, so we could call this kind of thing a map space or an exponential object. There's differing terminology, but basically think about all the different functions from this smooth space B to this smooth space A, the different functions which our theory allows, and imagine that they are sort of organized into this space. And so that's how we can think of this. So the first question I want to ask is, what would a point of a space like this look like? So if this space is the space of all maps from B to A, then a point of this space would simply be a map from B to A, okay? So let me make this a bit more down to earth. Let's consider the case where A and B are both equal to R. So in other words, let's think about this space, R to the power of R. And my question is, how can we think of this space? Well, if we just think about what our terminology means, we can say that this is going to be the space of maps from our smooth line to itself, okay? And so how are we to think about that? Well, let's just think about a map from the smooth line to itself. So here's a graph of this function here, which is x squared. So the way that this works is if we take any input x on our smooth line, then we take it and we square it, and that's going to be the output. X squared is equal to f of x. So here, this f here is a map from R to R. And so we could write that f is in R to the power of R. Or if you like, f is a member of this space of maps from R to R. Now, another way we can say this, sort of employing this kind of terminology, we could instead write the same kind of thing like this. We could say, well, we can think of f as a point in this space, which we're calling R to the power of R. And so now what I want to do is to introduce something called lambda notation. You see, I've really described this function like this. I've said that f of x, I've said that we have this symbol f, and then we're thinking of f as being a function, and f operates on a variable x in our smooth line, and it returns x squared. Now, there's a sort of notation which allows us to talk about things like this in a cleaner way. And this is called lambda notation. So this is the same kind of notation which is often used in lambda calculus. And it's really very pleasant sort of notation which allows us to talk about functions more easily. And so if we have this function f, and now I'm just going to think about f being a function from R to R, well, we could write this function f, which just squares its input like this. We could say that we could write this function f as lambda x dot x squared. And so what does this notation mean? Well, basically we can think of this that I've just written down as a kind of operator. And so think about this as some kind of machinery which is waiting for an input, okay? So just like if we had 7, and then if we did f of 7, that would give 49. Well, since we have this kind of equality, we can just write exactly the same thing, but with this in place of the f. So we could say that lambda x dot x squared of 7 equals 49. So all I've done is just replace f with this thing it's equal to. But what's really great is that this notation actually tells us exactly why this statement works, because the way that we interpret this lambda notation is that when we have lambda and then a variable and then a dot, then afterwards some expression, we can think about this as a sort of operator. And when we put something on the right hand side of it in brackets, that means that we're applying this kind of operation to this sort of input. And the way that we actually work this out is we simply take the input, which is the thing in brackets to the right, 7 in this case, and then we just use this as x. So the way that we can think about this expression, lambda x dot x squared, is this is an expression where we're going to take what we're operating on, which is the thing on the right, and we're going to look at this thing after the dot and replace all the instances of x with this input, okay? So let me break this down a bit more. This thing here is lambda notation for a function, and this thing here is the input. And so here's the input. Now this x here is what we call the bound variable. Now x is clearly a variable of type r in this case. It's something on our smooth line, but we say it's bound because it's kind of been exclusively reserved for usage within this kind of lambda notation. And this thing here is what I call the expression. Now the general idea is that when we apply one of these kind of operators to a particular input, all we do is we replace each instance of our bound variable, in this case x, which occurs within our expression, with the input, okay? So if we're doing this very symbolically, we just say, well, the answer is just going to be what happens if we take this x squared, but then we replace the x with 7. So the answer would be 7 squared, which we can simplify to be 49. So I'll give you another example. We could write lambda x dot x plus y plus x squared. And we could operate this on 2. And then the answer would just be, what happens if we take this expression and then we replace the x's with the input, which is 2. So then the answer would be y plus 6. And what's y? Well, that depends. Maybe we have another lambda operator, or maybe that's just another variable or whatever. So now we know this lambda notation, we're ready to talk about exponential objects in a more sort of general way. So firstly, let's carry on with this idea of this x squared function. So here's our function f. It's a function from r to r, and I tell you that f of x equals x squared. Now it turns out, as I'll justify a bit later, that this function f, we can also think of it as being a point in this space r to the power of r. And the way that we can write it is we can write it as lambda x dot x squared. And so this is actually a very special case of what can happen in general for exponential objects. So now let's look at the general case. So let's think about this kind of situation where we have three smooth spaces, A, B, and C. And now we have a function g, which is a function from A times B to C. So when I'm thinking about things like this, I like to have a definite example in mind, just to make it easier to kind of check that things are working sensibly. So we'll think about this in general terms, but our sort of definite example, which we can also keep in mind, is the case where A equals B equals C equals R. Okay? So in that case, g is going to be a function which takes into reals and returns a real. So that's a nice case because we can sort of draw it, okay? We can draw a graph of that kind of function. We can think, well, we have these two inputs. We have a copy of the smooth line, which is called A. We have a copy of the smooth line, which is called B. And so we have this kind of plane of input values. And then for any particular input value, there's going to be a certain value of the output. And so that defines this kind of surface. And so this surface is telling us, for example, if we pick a particular input A from space A and we pick a particular input B, then the height of this surface above that point in the plane is going to be g of A comma B. So the way I like to write this kind of thing is to sort of write in red underneath the function how it works. So it takes a value A in the space capital A, a value little b in the space capital B, and it returns this value g of A comma B, which is going to be a value in this space C. Now here's the absolutely critical idea, which really goes to the core of how exponential objects work in this kind of world of smooth spaces. Okay, so let's just put these reminders about what our inputs and outputs look like up there. So if I just move that over there, right, so now here comes the really crucial idea about how exponential objects work. The idea is that this kind of function, g here, corresponds to another function which we can write as g overlined, and that's a function from A to C to the power of B. Okay, so there's a lot of new things coming in here, so I'll take some time to explain. Firstly, what do I mean by this horizontal line here? So this is a kind of notation which basically means that mathematical objects above the line are in one-to-one correspondence with mathematical objects below the line. Okay, so we're talking about there being a kind of relationship, a one-to-one relationship between these two different things, or a bijection, if you like. So for every kind of function like this, we can find a function like this. And for every function like this, we can find a function like this. Okay, so the second thing then is, what is this function like? Well, it's going to take a value from this space A, and then it's going to return a value from this space C to the power of B, which is the space of maps from B to C. And so there's a couple of ways that we can think about this. The direct one is the sort of algebraic way to think about this, which is that the way that this G bar works exactly is it takes a value A from this space A, and then it forms this kind of map from B to C, which we can write as lambda b twiddle dot g of A comma b twiddle. Okay, so this twiddle here is just some decoration, because I want to record that this b here is a bound variable now. So you don't need to worry about what this twiddle means. I just prefer to put a little bit of decoration on this symbol to indicate that it's kind of involved with this lambda operator. And so the way that we can think about this G overlined working kind of algebraically is that this G overlined is a function which returns a function. Okay, so when it operates on a value of A, it returns this function here. Okay, it's ready to operate on a input from B and use this value A that it grabbed before and use that together with its input. So there's a very nice kind of geometric way to visualize what's going on here. So if we've selected a particular value of A, or if we're operating, say, G bar on a particular value of A, so think about, for example, this kind of diagram. think about that composition, well, here we've picked a particular point of A, and then we're doing this G bar on that point, and so that's going to yield a point of C to the power of B. And so in this particular case, we can actually get some rather nice kind of geometric idea about what's going on, okay? Because what we're really doing here, as you can see by this green diagram, is when we've selected a particular point A in our space capital A, then that's really defining for us a map from B to C, which we're sort of writing in this lambda notation. Now we can think about this geometrically by thinking about what happens when we cut this purple surface that I've drawn with a kind of plane which goes downwards through this point A. And so we're using this point A, and then we've got this kind of cut of our surface. And if you sort of move an amount B kind of along like this, then you can think about the height, then you can think about the height of a point which is kind of B along this cut which we've just made. And so you can see that this cut, which I'm now redrawing in orange, is basically indicating this kind of function here, which is ready to take in a value B tilde and return G of A comma B tilde. And so this is the basic idea about how exponential objects work in this category of smooth spaces. And so I think that's enough basic background to get the rough idea about what exponential objects are about. Now there's a lot more details that I'm not really mentioning here, and you can dig into my content about exponential objects in my category theory videos for a more kind of complete explanation of what's going on. But this kind of notation in black is really the kind of key idea, basically that we can convert between this kind of function G, which takes two inputs, an input from A and an input from B, and returns an output in C, and we can sort of convert between that kind of way of thinking of a function and this kind of way of thinking of a function here, where we're basically representing the same kind of function, but now we're thinking, well, actually, let's just use our first input A, and then we're actually going to return a function from B to C. But this function already kind of has this value A fixed now. So let's go back to this idea of this x squared function, and we can think about that a bit more clearly using this key kind of diagram here. So in particular, what we're thinking about is this kind of function which I'll call f, which is a function from R to R. And as I've said, it takes in an x and it returns x squared. Now what I can do is write a sort of equivalent function which works like this. We'll start with an input in this space 1 times R, and so there's only one value of this space 1, which is star, so the input must be of the form star comma x. And I mean, what happens when we do the product of our space with this space 1? Well, it doesn't really change the form of the space actually, so we could actually say that this space 1 times R is basically the same as this space R. And so we could just ignore that kind of star at the beginning, because, I mean, if you think about what happens when you do the product of two spaces, you're basically just like pairing the values from one space with another space. And when you do the product of a space with 1, that basically just means you're attaching a star to each value, which doesn't really change anything. Okay, so the way that we can formalize this kind of idea is to say that doing this kind of second projection here, P2, which basically just grabs the second entry from our pair and therefore sends star comma x to x. Well, we actually have that this kind of map is a special map called an isomorphism. So basically, we can think of isomorphisms as being one-to-one onto functions. A bit more precisely, we'd say that an isomorphism from a space A to a space B, say f, is something that has an inverse. So there's a function f to the minus 1 going the other way around, so that if we compose this function before this one, the result is the identity function of A. And if we compose this f to the minus 1 followed by f, the result is the identity function of B. So this is the normal kind of idea of an isomorphism. And when there's isomorphisms, and when a function f is an isomorphism, we sometimes denote it with a little twiddle, and it basically means that the two spaces involved are pretty much the same, or they can be converted into one another by continuous functions. I say pretty much the same in a very loose sense. For example, if you think about an ellipse or a circle, well, these are two different spaces, but there's a continuous function from the ellipse to the circle, and there's a continuous function from the circle to the ellipse. So in a sense, these two spaces can be deformed into one another. But often when we're thinking about spaces, when they are isomorphic, then when we think, but usually when we're thinking about these kind of data structures involving functions and whatnot, when two spaces are isomorphic, it usually means that they're similar enough that we can disregard the differences. So basically what I'm indicating here is that a space R is isomorphic to this space 1 times R, and this second projection here is giving us our isomorphism. So I'll complete the picture now and say that if we write this function f from R to R, then we can see that what's above this line is kind of similar to what's below the line, okay? So if you just think about what's this composition, well, it takes in a star comma x and it returns x squared. And the thing above the line, it takes in x and returns x squared. So these are two pretty similar situations. So we can just tidy this up a bit. We can just write this as the composition. It's the function f after p2, and it's a function from 1 times r to r. And now we can finally apply this kind of key correspondence that we get because of exponential objects. So we can say that this kind of function here corresponds to this other function, which takes 1 to r to the power of r. And we can write this as f after p2 overlined. And so basically we can think of this as a sort of point of r to the power of r. And it's basically just this function which is ready to take in an input and return that input squared. So this idea of exponential objects is beautiful in the extreme. It's actually an idea which can be generalized to all sorts of other situations which we're not looking at. But even if we're just thinking about the situation for this kind of category of smooth spaces, it's really a very pleasant idea. So let's think about something in physics. We'll think about a cloud. So let's call this cloud C. And then we'll suppose that we have some space. Let's call that S. So we could think of S as ordinary physical three-dimensional space. This cloud has all these particles and whatnot, and in a real situation, they're going to be in different locations in space. So if we're thinking about this cloud at a particular time, every particle of the cloud is going to be at some point in space, and there's going to be a sort of continuous map from the particles of this cloud to places in space. And so we can really think of a sort of way that this cloud is at a particular time as a sort of map from this space C to this space S. And this is really very pleasant, because if we think then about what this space S to the power of C represents, it has really quite a profound meaning physically. Because what is this space? Well, we could just say, oh, it's the space of maps from C to S, or we could say that this is really the space of possible positionings of this cloud. Every point in this space is a way that this cloud might be sort of in 3D space at a particular time. So if we consider a particular value f in this space S to the power of C, well, that's really sort of corresponding to a map from C to S, a particular way that these particles or values in this cloud are being associated with places in space, the places where they are. But it gets much more interesting when we also think about time. So the way that we can think about time using these kind of notions of smooth spaces is to think about time as basically corresponding with our smooth line. Okay, so basically if capital T stands for time, then we can just think of capital T being our smooth line. So we have this kind of smooth line of moments, 0 maybe representing the present and 1 representing one time step in the future, and so on. So the thing is then, in physics, of course, this cloud is going to exist in time and space, and we can represent this in a very pleasant way. So let's consider then what it would mean to have a map from T times C to S. Okay, let's think about, say, a map H. So what would that mean? Well, what this kind of map would be doing would be sending every time, little t, which would just be a real number basically, and every particle, little p, of our cloud to a particular place in space. Now this makes sense, right? So there might be a particular particle in a cloud, and then after a certain amount of time it will be in a particular place. So we could surely, so we can make this kind of, so we can think that there's this kind of map here, H, which is telling us where a particular particle is going to be at a particular time. But when this gets really profound is when we start to think about how our exponential objects works with this kind of notion. So let's apply this kind of critical correspondence here to our situation with the clouds. So try and memorize the basic form of this. It's pretty simple. We just take this B over here and we can just shift it up here. So in a similar way, we can take this thing on the right hand side here and shift it up here. So we can say that this kind of H here corresponds to another map, which we can write like this. Now this kind of thing is often called the transpose of H in general when we're dealing with exponential objects. So let's think about what this kind of map's like. It's now sending a particular time to a particular placement of this cloud in space. Okay, so it's going to, so what this is saying is that there's another way to view this situation, which is that at any given time t, we have this kind of way of placing the different particles in our cloud at particular places. And I think this is a really lovely kind of idea. So just as an aside, what does it mean to have a function from t into a space? Well, basically t is just our smooth line. So what's it mean to have a function from our smooth line into our space? Well, let's think about another case. What happens if we have a function from r to, let's say, r squared? Well, here's r squared, or a little picture of it, and then there's going to be a certain value that this function, let's say k, sends 0 to. So maybe this is k of 0 in our plane. And then maybe this here is k of 1, and this here is k of 2. But of course, this is a continuous function, so it's really just going to be giving us a path in our target space. So the way that we can think of a function from R into a space is basically just as a path in that space, because all the functions that we're dealing with are continuous. And so what this is basically saying is that another way we can visualize this kind of map here is as a kind of trajectory or path within this placement space. But I mean, these ideas are extremely deep. I mean, we'll get more into this later, but if you think, for example, say you had a problem that you wanted to work out how the center of mass of your cloud is going to change over time. So let's say you knew this kind of function h, which basically tells you the movement. Well, then you could transform your kind of view of the situation into something like this. And then at a particular time, you would actually want to have a kind of function which is telling you all of the kind of positions of all the particles in the cloud simultaneously. And then you could do something to that to actually work out where the center of mass of the cloud is at a particular time. But there's actually much more to this interesting situation, because there's another way of looking at things. So if we start with this kind of situation again, where we have this function h, well, there's another way that we can visualize what's going on. And that's basically just that we switch the order of the inputs, okay? So it turns out that this space c times t will always be isomorphic to t times c. Basically, if we just do the product in a different order, I mean, we'll have a different space, but it's going to be isomorphic to the original one. And so there's going to be a sort of corresponding function like this from c times t to s. And then if we again apply our idea of exponential objects, we can convert this into a function like this. Now this goes from c to s to the power of t. So what this kind of function is doing now is it's sending each particle p in the cloud to this kind of function here, which is ready to take in a time and then output h of t tilde comma p. And so basically what this kind of function is doing for us is it's sending, so basically what this kind of function is doing for us is it's sending every particle of our cloud to this kind of function which is describing the path that that particle is going to take through space. Okay, so this is our kind of third view of what's going on in this physical situation. And this kind of view could be useful if, for example, you wanted to, and this kind of view could be useful, for example, if you wanted to work out how the velocity of a particular particle changes over time. And you could basically do that by differentiating this kind of function. We'll get into this kind of idea later. So that's a sort of quick introduction to the ideas of exponential objects or map spaces. I could say a lot more, and I have a video on exponential objects which you can take a look at, but I think that those kind of bare basics will allow us to describe most things, and I'll try and talk through what's going on in subsequent examples. So these ideas should become clearer as we go on and look at more applications of them. So these spaces of maps are one of the best things that we have in this kind of theory of synthetic differential geometry, in the sense that exponential objects aren't usually something very easy to think about in geometry, but they give us a lot of power to explain different kinds of situations. And the other key thing, of course, is this kind of idea of infinitesimals, in particular nil square infinitesimals. So recall that we have this kind of space of nil square infinitesimals, these values on our smooth line, which have the property that if we square them, we get 0. So these kind of nil square infinitesimals, we can think of this as part of the smooth line, very close to 0, or we can actually think about this as being a space in itself. And let's say we have some other space S. So, for example, maybe it's a sphere. It could be any space at all. Well, what would it mean to have a map V from our space of nil square infinitesimals to S? Well, it turns out, as we're going to see, that we can really think of such a thing as a tiny little vector inside our space. Now, I'm glossing over a lot of details, and so I'm going to talk about all these things in a more systematic way later, but just to tell you, one of the most important ideas in this theory is the idea of what the space S to the power of delta might look like. Okay, so what would be a point of this kind of space? Well, it would just correspond to a function from delta to S here. In other words, a point of this space here, S to the power of delta, is just going to be a map from the nil square infinitesimals to S. But the thing is that we're actually going to see later that any such map, for example this V, we can really think of it as a sort of so-called tangent vector within our space. So it's kind of easy to at least get an intuitive kind of idea of what's going on here. Okay, so firstly, let's consider what it would mean to have a function, let's say u, from R into S. We'll think of S as being the sphere. Okay, so then we can think of R here as basically being a sort of timeline. We'll call it capital T. So then this kind of function u, we can just think of it as being a sort of path on the sphere. Okay, it sends 0 to where we are at time 0 on the sphere, then we'll be at another place at time 1, and another place at time 2, and so on. So here's our line, here's 0, and then at each point on this line, that corresponds to a time. So let's say we've got 1 here as well. And so we'll be at a particular place u0 at time 0, and a particular place u1 at time 1, and so on. So now what we can do is consider this other situation where we just have this function v from our space of nil square infinitesimals into S. So now we're just interested in what's going on for these inputs that are very close to 0 within these kind of nil square infinitesimals that are actually so close to 0 that if we square them, we actually get 0. And so it turns out that just like a function from R into our space looks like a path in our space, so a function from delta into our space just looks like a little vector. So we're going to see much more about this very shortly, but in a nutshell, the idea is that we can think of this space S to the power of delta as what mathematicians might call the tangent bundle of this space S. And we can kind of dig into this space in a very easy way and use it to construct some other very interesting ideas, like ideas about vector spaces and velocities and all sorts of things. And you'll probably be amazed about how easy this kind of theory is to deal with. But I've really just been trying to give a flavour of some kind of up-and-coming concepts. Now I want to talk about something much more definite. So what I want to do next is to make this idea of thinking about something like S to the power of delta much easier. So I'm now going to consider a simpler case, which is where we're thinking about S as being the plane. So what's r squared to the power of delta? Or more precisely, what's a point of this kind of space? So in other words, how can we think of a map from our nil square infinitesimals to the plane? Now, if what I've been saying is true, then we ought to be able to think about this as just being a sort of little tangent vector in the plane that sort of points out of v of 0 in a particular direction, and this vector has a particular magnitude. So think about, for example, those little arrows that they use to indicate how the wind's blowing on weather forecasts. So we want to see if we can actually get at this kind of intuition. Now, in order to do this, let's revisit. So we're going to get there, but we'll do it systematically. So let's start by revisiting this kind of central axiom that we're using in synthetic differential geometry. So this is what we call the principle of micro-affineness. So if you remember the idea is that if we have some map h star from our nil square infinitesimals to our smooth line, then basically it looks linear. Okay, so there's going to be a unique value b such that for any input epsilon, which is a nil square infinitesimal, we have h star of epsilon is equal to h of 0 plus b times epsilon. So our input is some epsilon in here, and our outputs are given by this straight line plot, where this straight line will have some gradient b. So we discussed last time about this idea and about how it sort of forms the kind of foundations for thinking about things like differentiation. But what I want to do now is to look at this kind of thing in a bit of a different way. So in particular, let's now consider this space, which we could write as r to the power of delta. So what is this? Well, this is the space of maps from nil square infinitesimals to our smooth line. And so it's a little bit of sloppy notation. And so it's slightly sloppy notation, but we can think of this kind of h star thing here. We can just think of it as a sort of value in this space, r to the power of delta. Now here's the big claim. The big claim is that r to the power of delta is actually going to be isomorphic to this space r times r. In other words, every map from r to the power of delta can be described by two numbers, and here they are. The y-intercept, h of 0, and the gradient, b, okay? And that's because each of these kind of functions from delta to r is basically a linear kind of function, or it has a kind of straight line plot. So basically, if you give me a map h star from delta to r, then I can give you two numbers, a, which is equal to h of 0, and b here. And those two numbers are sort of representing that function. So basically what I'm trying to say here is that there's an isomorphism, let's call it L, and L is going to send H star to these two numbers, A and B. And these numbers are such that we're going to have that H star of epsilon is equal to A plus B times epsilon. And that works for any epsilon in delta, okay? And this L here is an isomorphism, okay? Basically meaning that it has an inverse, okay? So we can sort of undo this operation quite easily. So what I'm trying to say here is that this function L here has an inverse. So we could call that L to the minus 1. And it's easy to describe how this works, okay? So it's going to take in an input, which is a pair of real numbers, say A and B, and then it just forms this kind of function here, which we could write as lambda epsilon dot A plus B times epsilon. So basically this inverse thing here just uses our two numbers to build this kind of linear function from nil square infinitesimals to the line. So this is basically a sort of alternative way to think about this axiom. And it's really interesting because if you think about it, this is really underlying our idea of movement and velocity in some sense, okay? So basically what this kind of relationship is saying is that an infinitesimal path on our number line can be described by a position A and a velocity B. Okay, so let's just think about a nice simple example so we can get our heads around this. So here's the line, and then let's suppose that at the present, whenever the present is in our thought experiment, we have an ant. And this ant is, let's say, 7 centimeters to the right of the origin. So this is what's happening when t equals 0. And let's suppose that this ant is moving somehow on the line, okay? And we're interested in how this ant's moving very, very close to the present, okay? So so in this thought experiment, we're going to imagine that the way that this ant is moving very sort of close to the present is described by some map, let's say K, from the nil square infinitesimals to our smooth line. So this thing on the right here, we can think of this as the space that this ant's moving in. And we can think of this space of nil square infinitesimals as corresponding to times very, very close to the present. Okay, so we could imagine that k of 0 is equal to 7. So this map is sending the value 0 in delta to this number 7. And so alternatively then we can sort of think of k as being a point in this space of infinitesimal paths on the line. And then what we can do is apply this kind of isomorphism that I was just talking about. And so we can then extract this kind of pair of numbers. And so what we'll find then is that corresponding with this infinitesimal path k on our smooth line would have this pair A and B. And A would be where this ant is at the present, so that would be k of 0, and that would be 7 in this thought experiment. And then this B here would be giving the velocity of our ant. So at a sort of infinitesimal time epsilon, we'd have that the position of the ant is going to be equal to k of 0 plus b times epsilon, or if you like, a plus b times epsilon, or if you like, in this case, 7 plus b times epsilon. And so we can see here that the kind of description of the ant moving as a sort of infinitesimal path corresponds to this kind of description. So we can see that this kind of way of describing the ant's movement as this kind of infinitesimal path corresponds to this kind of position, comma, velocity description of our ant's motion. So this kind of way of thinking about infinitesimal paths has so many implications for different areas. So we're going to see that it helps us to think about ideas of curvature, it helps us to think about ideas of physics, even generalizing laws of motion. All sorts of ideas come together here. So we're going to talk about these things in much more detail later. And what I'm about to write might not make much sense at present, but I'm just going to write it anyway, and then we'll get on to something else. So firstly, if we have two spaces A and B, and they're isomorphic, in the sense that there's an isomorphism, let's say F from A to B, well, we could write it like this, or sometimes we just write this kind of, notation, which basically is just notation for saying that these spaces A and B are isomorphic, in the sense that there's a isomorphism from one of the spaces to the other. So now, basically, the way that we can think about an infinitesimal path on the plane, well, we can think about it as follows. We can say, well, the infinitesimal path can be thought of as a function from delta to r squared, or we can think of it as a point in this space r squared to the power of delta, the tangent bundle of the plane, if you like. Now it turns out that we can alternatively write what's on the right hand side as r to the power of delta all squared. And now we can apply the isomorphism that I was just talking about to rewrite this as r times r all squared, which is basically just r to the power of 4. And so what we can see here is that an infinitesimal path on the plane corresponds to a 4-tuple of numbers. In particular, our infinitesimal path ends up being described by a sort of pair of x comma y, which gives a position, and vx comma vy, which give the sort of horizontal and vertical components of the velocity. So it kind of makes sense if you think about moving in a plane over a very small amount of time, that kind of movement can be described by giving a sort of position and a velocity, and you'll need two numbers to describe that position and two numbers to describe that velocity. And you get all of these ideas coming out of this theory explicitly in a very easy kind of way. And so when we want to describe our movement in the plane, well, that x comma y would be the sort of base point, v of 0, of our infinitesimal path. And then this kind of vector that we draw would have these two components, vx and vy, which would be these sort of components which indicate the kind of direction and magnitude of this kind of vector. Okay, so I'm trying to fight the urge to show you too many of the kind of amazing ideas that come from combining exponential objects with infinitesimals, because there's so many amazing ideas to do with curvature, manifolds, dynamics, and so on. And I just can't resist showing you, and I just can't resist giving you a little preview of one of the other major ideas, because in my opinion, it just makes so much of what you do in the study of dynamical systems and vector fields and so on so much easier to think about. To me, it really gives a much simpler kind of idea of what differential equations are all about. Okay, so the big idea is basically, what is a vector field? So let's suppose we have some space S, and we're interested in describing what a vector field on that space S is. So here's an example. This is the plane, and we're to imagine that there's a little arrow giving us a sort of direction of a kind of, say, a flow of a fluid or something on this plane. So every point in our space has a little arrow associated with it. And so it turns out that we can define what a vector field on our space is in a really easy way. So basically, a vector field for us, I mean, we're going to see this idea explained more carefully later, but basically it corresponds to a map phi, which takes in a point in our space S and a nil square infinitesimal in delta, and it returns another point in our space. Okay, so basically you can think of this as sending a starting point x and an amount of time epsilon to a new position, which is basically what we get by moving epsilon along the vector at x. And this is fine because if we're choosing our epsilon to be a nil square infinitesimal, in the sense that epsilon squared is 0, well, epsilon's so small that we are literally just sort of moving along this vector from this point x. Now, what I'm saying here might not be... So this is our idea of a vector field, and so in order for this kind of thing to be describing a vector field, what we want is that this condition holds true. So we want that if we choose our nil square infinitesimal to be 0, and we do phi on a point x with our sort of mini time as 0, then we return x again. So that's basically a fancy way of saying that the kind of vector associated with a point has its kind of base at that point. Or in other words, the little arrow associated with any point x is an arrow which emanates or starts from that point x. So basically, all this definition is saying is that a vector field is simply a map which sends every point of our space, an infinitesimal, to another point in our space, in such a way that when we set our infinitesimal to 0, this map always sends the input point to itself again. Now, there's several amazing things that you get out of looking at vector fields like this. One of them is that we can write down the idea of basically what it means to solve a differential equation, or to find a kind of flow line, a sort of trajectory which follows our vector field. Well, we can say what that means in a very, very succinct kind of way. So this thing I'm drawing in pink here, this is an example of a flow line, C. And in general, we can define a flow line or a solution to the sort of differential equation which is described by this vector field, basically. Well, we can describe it like this. A flow line is just a map where we send every point of our space and every time, where time is basically a value on the smooth line, to another point in our space in such a way that this kind of equation holds. So we have that for any time t, which is a real number, and for any nil square infinitesimal epsilon, we have that the position that we're at t plus epsilon is equal to the position that we get to by starting at c of t and then moving this kind of infinitesimal amount epsilon along our vector field. So I know I'm rushing through this and I'm going to come back to these ideas in more detail, but I just can't resist showing you a kind of glimpse of how easy it is to think about vector fields and differential equations. Now, if you don't know what vector fields or differential equations are all about, don't worry, we're going to revisit this kind of idea much more gradually later. So now I want to talk about something quite different, which is also very important, and it's the other kind of big thing that we like to do in calculus, which is integration. So what we're going to have a look at now is how we can determine the area under a curve using our theory of infinitesimals. Okay, so remember we're writing delta to denote the x in R, which have the property that x squared is 0. So let's suppose we have this map f from R to R, and what we're interested in doing is calculating the area under this plot. And we'll call that area A of x. So that's the area under our curve. So that's the area under our curve from 0 to x. And so to put this into the ordinary notation of calculus, we could say that A of x is going to equal the integral from 0 to x of f of x dot dx. Now, if you don't know what this notation means, don't worry, we're not going to be really using it at present. The important thing is, how do we work out this area, A of x? And the key idea here is that we're going to consider some nil square infinitesimal, epsilon. And we're going to think about what happens if we increase x by epsilon. Okay, so this value here, this is x plus epsilon. And so now what we want to do is what's the value of A of x plus epsilon. And we can kind of work this out visually, okay? Because we're really talking about this kind of area now, which is just this purple area plus this little extra strip here. And so we can say that A of x plus epsilon is going to be A of x plus something extra. And what's this extra thing? Well, the height here, look, this height is going to be f of x. And so we can kind of break this extra area into two parts. So there's going to be the area of this rectangle and the area of this other region up here. Now, the area of this rectangle is easy to calculate. That area is going to be epsilon, which is going to be the width of it, times f of x, which is going to be the height. So we're going to have that area, and then we've also got this other little area here, which I will call S, okay? So that's our formula. What I'm saying here is that the area under the curve from 0 to x plus epsilon is going to be equal to this purple area here plus this area of this rectangular strip, which is epsilon times f of x, plus the area of this tiny little triangular-like thing here, which I'm calling S. And now what I claim is that this area S is actually going to be 0. So let me see if I can convince you of that. Let's imagine zooming in and looking at this area S in close detail. So let me see if I can convince you that this S here is 0. So if we zoom right into our picture, the area of this black triangle is going to be S. Okay, so let's think about this black triangle. We know that this dimension here is going to be epsilon. And we also know that the height of the bottom of the triangle is going to be f of x, and the height of the top of the triangle is going to be f of x plus epsilon. Now we also know that this is going to equal f of x plus epsilon times the derivative of f at x. And if that doesn't make sense to you, you can look back at the previous video where we talked about differentiation, because this is basically our sort of definition of the derivative of our curve. And so what that stuff basically means is that the height of this triangle here, and so what that stuff basically means is that this height here, this triangle, is just going to equal epsilon times f dash of x. And so now we can work out the area of our triangle. And the area is simply going to be the base times the height divided by 2. So that's going to be, so in other words, what we have here is that the area of our triangle, S, is going to be the base, which is epsilon, times the height, which is epsilon, times f dash of x, divided by 2. Well, that's equal to epsilon squared times something, so it's going to be 0 times something else, so it's going to be 0. So S is 0. And so in other words, we can forget about this extra bit here, and we can literally say that the area under our curve up to x plus epsilon is just actually equal to the area of our curve up to x plus this extra sort of rectangle, which we get by just multiplying our nil square infinitesimal epsilon by f of x. But now here's the really nice thing. But now here's a really neat argument. The thing is that this function a here for our area, well, we can think of that as a function from r to r. And so this function is going to have a derivative, which we can call a dash. And what's the definition of a dash of x? Well, a dash of x is the unique value such that we've got that this equation holds for only nil square infinitesimal epsilon. Okay, this is just from our definition of a derivative. And so if you think about it, that then implies that we've got to have that the rate of change of our area is equal to f of x. Okay, in other words, what I'm saying here is that this area function is the function. In other words, what I'm saying here is that this area function, a of x, actually has the feature that the derivative of this area function is itself f of x, which is basically getting towards the fundamental theorem of calculus. And so basically what we've done now is we've derived two important aspects of this function a of x giving us the area under the curve. One of them is that the derivative of a of x is going to equal f of x, and the other one is that a of 0 is going to equal 0. Okay, the area under our curve from 0 to 0 is just nothing. Okay, so it turns out then that from this the area is uniquely defined. Okay, so we can see this, and we can see that this follows from the constancy principle, which is another one of our kind of fundamental axioms that we discussed before, which basically says that if we have a map, say from if we have a map from R to R, let's say a map K, and we have that the derivative of K is 0 everywhere, then this map K has to be constant. Okay, so let's see how we can use that to actually work out now that these kind of integrals or area functions that we've been discussing are uniquely defined by these properties. So in particular, let's suppose that we have two different functions, a1 and a2, and these are both functions from R to R, and let's say that both of these functions satisfy these properties, and then what we want to do is show that these two functions are actually equal. So we're going to assume that a1 dash of x is equal to f of x is equal to a2 dash of x for all x, and we're going to assume that a1 of 0 is equal to a2 of 0 is equal to 0. And now the point is that, and so what I'm then going to do is to use the constancy principle to infer that a1 is equal to a2, thus showing that making these kind of constraints essentially uniquely defines how this function a has to work. So the way that this little proof works is that we'll define b of x to equal a1 of x take away a2 of x. And so now if we consider the derivative of b, it turns out, it can be shown, that that's going to equal the derivative of a1 take away the derivative of a2. But now we know that that's 0, okay, because we're assuming that these two things are always equal. And so now what we have is that this function b from R to R has derivative 0. So we know from our constancy principle that any such function that has a derivative of 0 everywhere has to be a constant function. So that means that there is going to exist a value in R which is such that b of x is equal to that value for all x. We also know that b of 0 is a1 of 0 take away a2 of 0 is 0. So we've got to have that v itself is 0. So that means that b of x is got to equal 0 for all x. And remember, that's a1 of x take away a2 of x. So now this cute little proof is over because we've basically got that a1 of x take away a2 of x is 0. And hence we have that a1 of x is equal to a2 of x. So that's just a little argument which says that these kind of conditions of saying that the derivative of capital A is f and capital A of 0 is 0 are enough to kind of uniquely define this kind of area function. So if you want to put this in terms of ordinary calculus, we've basically shown that this kind of idea of integrating f of x from 0 to x is properly defined. At least we've given a hand-wavy argument for that. Okay then, so the point of this course is really to try and reveal some of the powerful things that you can get out of looking at problems of calculus and physics and whatnot using this synthetic approach to differential geometry. And there's certain things that I think really highlight this. And so a lot of this video, I've kind of been stretching maybe a little bit too far as how quickly I'm introducing the concepts. I don't like usually to introduce things without laying the proper foundations. However, in this case, the kind of things that we can do with these methods are so profound, in my opinion, that it gives a lot of good motivation for the sort of digging around at the foundations and making sure the theory is solid and all of these kind of things that one can do later. And so for that reason, I want to kind of push ahead and to go through a couple of other things which I think really highlight some of the powerful aspects of this theory of synthetic differential geometry. And so what I want to do is to talk about the behavior of something in physics, which is called a harmonic oscillator. So don't worry if you don't know any physics. I'll try and make it clear what's going on. On the other hand, this, if you're very new to calculus and a lot of these concepts, and if what I'm saying seems too complex, don't worry about it too much, because we're going to sort of be able to come back at these kind of situations when we've got more experience of the basics. But all that being said, let's go. So we have this kind of system where we have a mass on a spring. And so we assume that the spring's attached to something. We'll ignore gravity. And for this particular example, we'll ignore friction and all the rest of it, so that we have a very simple model of the movement of this mass on a spring. And so we have the usual equation from physics, which is that force, which I'm denoting by capital F, is equal to mass times acceleration. And so the position of this mass on the spring is recorded by this number x. So we could think that there's a particular sort of zero setting, which would be where this mass would be when it's at rest. In other words, when we just let the system settle to its kind of equilibrium or fixed point. And then this number x is measuring the displacement away from that kind of 0 point. And so at any particular time, we can describe where the mass is by this displacement quantity x. And so basically this mass is moving along on the line, and what's going to happen is it's going to bounce backwards and forwards over time. So the rate of change of the displacement with time is going to be the velocity, and again that's a signed quantity, so the thing might be going to the right or to the left. And then the rate of change of the velocity, so that would be dv by dt, we can also write that as d squared x by dt squared, and that's the acceleration. Okay, and Newton's law says that the force is equal to the mass times the acceleration. So we can just think of that, if we like, as a definition of force. But we also have a particular law in physics called Hooke's law for this kind of setup where we have a mass on a spring. And this says that the force is equal to some constant k times -1 times the displacement. Okay, so this is basically Hooke's law. It says that the force is proportional and in the opposite direction to the displacement. And so this number k is sometimes called the spring constant. And so we have this setup, and basically, given this kind of relationship, given that basically that the acceleration is equal to, given this kind of relationship, which basically boils down to saying that the acceleration is equal to -1 times a constant times the displacement, well, given this, what we want to do is to sort of solve this system of differential equations and to find out how this displacement is going to vary over time. And so we can do this as follows. Firstly, what we're going to do is think about the derivative of x with respect to time. Okay, so we can think of this displacement as a function of time, and we can take its derivative. So we could write that as x dash of t, and we're going to have a name for that. We're going to call it v, or v of t. So that's going to be the velocity. And so basically by definition, v equals dx by dt. And also, if we sort of take this law, we can rearrange it to get that the acceleration is equal to -k over m times x. And the acceleration is the rate of change of the velocity. So we've got that dv by dt is -k over m times x. So what we can think of now is that we have these two kind of quantities, the displacement and the velocity, and we have these two equations, these two differential equations, which are saying how both of these things change depending on the current, velocity, and displacement. And the normal kind of approach to thinking about this that you'll find in textbooks on dynamical systems and so on, the kind of classical approach is just to say, well, we can basically form a kind of vector field with this. And so there's these kind of two quantities, x and v, and if we have particular values of x and v, then these two equations here tell us what the rate of change of x and v are in terms of those things, and that basically defines an arrow in this vector field. And then what we want to find are the kind of trajectories which we'd follow when we follow the kind of vector field, when we follow these kind of flow lines around. And this is basically how we're going to look at the system too. But we're really going to look at this system from this kind of perspective of using nil square infinitesimals. And I think it reveals a lot about the nature of differential equations. And then after we've done this, we're going to look at some fascinating ideas of how to generalize laws of motion. Okay then, so let's have a look at how we can analyze this kind of situation from the sort of synthetic differential geometry viewpoint. So firstly, we're interested in how this system moves. So we could think that there's a point on the end of this spring. Maybe we think of the mass as being point-like or something. And so we can think that there's a sort of line that this thing's moving on, and at any particular time, this point on the end of the spring is at a particular location. So we have a space, which we can call S, and we can basically model our space as our smooth line R. So we can say space equals S equals R by definition. And the other thing that we want to model is the velocity, and let's call that V. And again, we can model that with our smooth line. So if we're working in metric units, maybe our particle on the end of a spring is moving at 2 meters per second or minus 3 meters per second, which would mean it's moving to the left, and so on. And so now we can do our normal kind of isomorphism, okay? Because we're interested in how our because we're interested in how our particle is going to move through space. So let's consider an infinitesimal path in S. So in other words, S to the power of delta. Well, that's R to the power of delta. And using our normal kind of isomorphism, that's isomorphic to R times R. So this is the usual kind of idea that if we have some map, let's say H from delta to R, then that's going to correspond to A comma B, such that H of epsilon is equal to A plus B times epsilon for all epsilon in delta. And so that second B, that's really a rate of change of our location with time, if you like. So we can really think of that as a velocity. I mean, it's a point on the smooth line, basically. It's a value on the smooth line, really, but we're having that the smooth line is equal to V, and that is a velocity. So we can just think of this as R times V. I mean, it's basically just a rewriting of that R on the right-hand side. And this R on the left-hand side, this is where this A lives, and this A is H of 0, and this is the place in our space where our infinitesimal path starts out. So this R on the left, we can just think of it as S. So these kind of steps at the end are really just renaming stuff. There's not really any new maths there. But the idea basically is that our infinitesimal path in space corresponds to a sort of position and velocity allocation. So now the next thing is that we have a law of motion, basically. And I think this is perhaps the most interesting part of this, because we're really saying that what we're really saying with these kind of equations is that our infinitesimal path can be described by saying the current location as well as the velocity. And so if we think of that as a configuration, let's call it a configuration, okay? So it's what we need to specify what's going on at a particular time in our system, really. It's like a point in the phase space, if you like, to use dynamical systems talk. And so a sort of configuration at a given time is a allocation of a position and a velocity, as in a point in S time, as in a value in S times V. And our law of motion is saying what the kind of configuration will be. And our law of motion is basically saying that if we know the current location and velocity, then a time epsilon later, what's going to be our new location and velocity. And so that's our law of motion. And this is basically the way we're going to write it. What we're going to be saying is how the displacement x and the velocity v are going to change over a small amount of time. And in fact, what we're going to write is that the displacement just changes because of movement due to the velocity that we already possess, and the velocity changes because of the acceleration that happens because of Hooke's law, because of the law of motion of the harmonic oscillator due to the force and so on. And so basically we can think of the law of motion as being written like this, if we like. And so we could think of the law of motion like this, but using the equalities above, maybe it's easier to think about it in this kind of form, like I've been discussing. And so in this case, we can think of our law of motion as I'm indicating here. So basically, in this case, if we know the current position and the current velocity, and we have an amount of time epsilon, then in an epsilon amount of time in the future, we can find the new position by applying this function L1 star to these three quantities, and we can apply this function L2 star to find the new velocity. Okay, so basically in this situation, we can kind of decouple how the velocity and how so basically in this particular system, we can decouple how the displacement / position and the velocity are changing. In fact, we can see this from our earlier kind of equations up here. Anyway, this is actually the law which is telling us how the position is going to change over time. And so what this is saying is that if we know the current position P, okay, it's the same thing as displacement. So maybe I can just write P equals X. Okay, so I'm calling it X for I'm calling the same thing X or displacement or P or position. I mean the same thing where the spring particle is on the line. Okay, so if we know the current displacement P and the current velocity V, then an amount of time epsilon later, the new position of our particle is just going to be equal to P plus epsilon times V. And in fact, we can get this law of motion. And in fact, this law of motion L1 star is a very natural kind of thing. It's basically a sort of inertial law. And we can even get it directly from our kind of isomorphism. So remember, we have that S times V is going to be isomorphic to S to the power of delta. So let's call that isomorphism theta there. And then by the properties of exponential objects, we can rewrite this kind of map as this map from S times V times delta to S. And in fact, that's exactly what L1 star is. So that L1 star is telling us how the new displacement can be determined a small amount of time later, given the current displacement and velocity. And the other part of this is determining the new velocity. And this is basically given by Hooke's law. Okay, so what L2 star is doing is it's sending the current displacement P, velocity V, and the amount of time epsilon we want to look into the future, and then it's giving us the new velocity, and that's just going to be equal to the current velocity V plus this nil square infinitesimal times the acceleration. And we have from our previous physics law that this acceleration is going to be equal to minus k times the displacement divided by m. So you see that we get this kind of basically a law of motion here. And the thing is that this is actually going to be a vector field. So what we're really doing here So a way that we could rewrite this is we could use the properties of exponential objects, and we could rewrite this as an arrow like this. And what we're doing is we're sending every point in this configuration space to a vector in such a way that the kind of base point or starting point of the vector associated with a given point in the space starts at that point in the space. So basically we've got a family of arrows in our S times V plane, which is giving us this vector field. And then all we want to do is to solve this for the flow lines. And it turns out that those flow lines are exactly the kind of solutions to this system of differential equations. So we've just seen how we can encode these differential equations as a sort of vector field. So now we just need the idea of a solution or a flow line, and basically that we can think of time as R, our smooth line again, and a solution. Let's say we're interested in a solution where the initial position of our particle is p0 and the initial velocity is v0. Well, a kind of solution then is going to be a map from our timeline t to our configuration space s times v, and we want to have that it sends 0 to p0, v0. So this is saying that the initial displacement and velocity are properly set. And we also want to have this kind of condition for a flow line to be met, which says that where we are on the flow line at t plus epsilon is basically where we get, if we take where we are on the flow line at time t, and then we move epsilon along this vector field, which is described by this law of motion L star here. And then it turns out that this is actually the solution to our system. And so basically this is just how we solve this kind of system of differential equations. And we just get that the solutions, the flow lines, are these kind, and we just get that the solutions, the flow lines, are these kind of circles about the origin. Because in this kind of perfect harmonic oscillator where there's no kind of energy loss because of the assumptions we've made, basically our spring's just going to bounce forever, and the amount of energy we give it initially is going to determine the kind of radius of this circle, which we're just going to go round and round in this kind of flow line, this trajectory in the phase space or the vector field, which is representing this system of differential equations. So I think that this is really interesting. Because all of these kind of ideas can be generalized massively, okay? So I've said about this before. So another idea that we have is this one that an infinitesimal path in the plane can basically be described by a position in the plane together with a velocity in the plane. So those would be four numbers, 2 to give the position and 2 to give the velocity. And in a similar way, a kind of vector in n-dimensional space can be described by 2 points in n-dimensional space, one giving the sort of base point of the vector and the other one describing its direction and magnitude. And so now let's go back to thinking about the cloud, okay? So you may recall earlier I was talking about this kind of example of a cloud and how we can think about the motion of the cloud and how it relates to space and time using exponential objects. So what I'm really doing here is I'm repeating some of the. So this is something that Lawvere considers in one of his papers where he talks about physics, and he talks about generalized laws of motion. And so this is something that I wanted to talk about now. So remember, we have this space S, which we can think of as physical space, and we have this space C, which we can think of as representing the particles of our cloud. And so we can think of a point of S to the power of C as a placement of our cloud in space. And so when we think about S to the power of C, all to the power of delta, that's going to be an infinitesimal path in our space of cloud placements. Or if you like, you can think about a way that the positions of the particles of the cloud might change over a very small amount of time. Now, we can rearrange this to write it as S to the power of delta to the power of C. And then we have S to the power of delta here. And using a kind of idea sort of similar to the notions I've been talking about here, under the appropriate assumptions, we can basically rewrite this as, we can basically rewrite S to the power of delta, this infinitesimal path in our space. We can basically think about this S to the power of delta, this space of infinitesimal paths in our space, as S times V. So basically what we're saying here is that we can think of an infinitesimal path in space as being kind of represented by a specification of a position S and a velocity V. And so then if we can write S to the power of delta as S times V, where V is a kind of space of velocities, then we have that S to the power of delta all to the power of C is going to be isomorphic to S to the power of V all to the power of C. And then we can rewrite this as S to the power of C times V to the power of C. And so basically the idea here is that we can think of our infinitesimal path in our kind of placement space of the cloud as a sort of way that the locations of the particles as a sort of allocation of positions to our particles of the cloud, together with an allocation of velocities to our particles of the cloud. And we'll call this now our configuration space. So now, for us in this case, a configuration means an allocation of positions to our particles of the cloud and an allocation of velocities to our particles of the cloud. And so now we can think about a generalized law of motion. So that would be a sort of arrow from x times delta to delta. So basically it would be a way that we could determine the placements of the particles of the cloud and the allocations of velocities of the cloud a small amount of time epsilon later, given the current allocations of placements and velocities of the cloud. So if the current positions of the cloud were governed by a function f, and the current velocities of the cloud were governed by a function g, and we have an amount of time epsilon, then given those things, we could, using a law of motion perhaps, determine the new locations of the particles on the cloud and the new velocities of the particles on the cloud, which will be present a small amount of time later. Now, I think one of the fascinating things about this is that it's such a general way of thinking about laws of motion. We're basically saying that things are changing and we're getting the idea of velocity straight out of infinitesimal paths. And we can do this in a very general way. So, for example, if we think about a surface, we could describe some surfaces by maps m from r squared to r cubed. And if we think about how m would lift these kind of infinitesimal vectors into vectors within our surface, then we can use those vectors to describe velocities. So we can kind of generalize some of these arguments and find ideas of velocities for more general kind of spaces. Indeed, the ways that we can think about manifolds and tie them together with velocities and think about derivatives is much cleaner in this synthetic differential geometry. But anyway, what I really wanted to say is that this kind of idea that we can think about placements and we can think about infinitesimal paths in a placement space, and we can write those in terms of velocity, and we can think about how those kind of resulting configurations might change over small amounts of time to give us laws of motion. I think this is a very deep idea. So I've been talking just now about this example where C here, this space C would be a space of particles, and S is ordinary 3D space. Now we could have a different kind of situation where perhaps C is a load of information and S is some kind of memory. And then we can think about how computers run. And maybe we could think about some kind of laws of motion by which computer programs might change. Maybe there's some kind of optimization involved. Maybe one can make some kind of generalized laws of physics which could optimize a kind of program to a specific end. You can also encode ideas like gradient descent, using some of the kind of operators from the normal kind of vector calculus. Another thing you might want to do is think about a kind of system involving how maybe people or beings are organized. So maybe C represents a space of situations and S represents actions. So then a point in S to the power of C would be a map from situations to actions. And maybe a person's personality could be kind of reflected in how they act in different situations. The example that we've just been looking at with the harmonic oscillator would be where C is just this 1 point space and S is just a line. You can also look at the case where C is space and S is temperature, and then you can get the kind of things like, and then you can model things like the temperature equation, and then you can model things like the heat equation, which is a partial differential equation, which you can think of as evolving in infinite dimensional space. So these kind of ideas of generalizing laws of motion are very rich, and it's something I'll hopefully have time to come back to and talk about in an easier to understand way when we've covered more topics later. The final thing I wanted to say might seem a little bit kind of cryptic, but I think it's extremely interesting. And that is, what about this space delta to the power of delta? So this is the space of maps from our nil square infinitesimals to themselves. And it turns out that if we consider all of those maps which send 0 to 0, those form a kind of space. And it turns out that, in fact, that space is isomorphic to the smooth line itself. So I think this is a really profound insight of William Lawvere's, that basically, if you think about maps from the nil square infinitesimals, basically delta is so small that maps out of it kind of make these little regions that don't bend. But if we consider maps from the nil square infinitesimals to themselves, you can think of those as basically, well, each of those kind of maps has the form that V of epsilon is going to be equal to B times epsilon for all epsilon in delta. So for every such map, there's going to exist a B a particular B for which this is true. And so basically each of these kind of zero preserving maps from delta to delta, if you think about delta as a very small time interval, like a moment, then you can think of it as a map from the moment to the moment, which is either speeding things up or slowing things down, but always sending now to now. And it's remarkable that that whole kind of it's extremely remarkable that that kind of map of zero preserving maps is basically isomorphic to the smooth line itself. And so this is similar to what Euler observed many hundred years ago, which is basically this idea that we can think of the continuum itself as a kind of space of ratios of infinitesimals in a sense. And so it's really remarkable because this gives a sort of totally different way to think about what the continuum actually is, and suggests that perhaps the nil square infinitesimals themselves might be the fundamental kind of mathematical object. And there's various other things that William Lawvere found out, which do sort of seem to indicate that from a kind of category theoretic view, it might be easier to define the nil square infinitesimals than to define this kind of smooth line in certain settings. Okay, so I'm aware that this video is getting rather long, and so I want to just very quickly just say a few final things about things that you can do in this wonderful kind of world of smooth spaces. So one thing to say is that it's really worth looking at these kind of maps which go from map objects. I mean, these are the kind of things we've been focusing on when we've been looking at laws of motion. These are the kind of things which physicists call functionals. These are the kind of things which can be used to talk about how differentiation works, how integration works, how you work out the centers of mass, and so on. Another thing I want to say is about parts. Now, one of the things about these kind of smooth spaces is that we have a special kind of smooth space called omega. So if we just think about set theory for a moment, the kind of version of this in set theory, which is actually which actually works a little bit differently, is the so-called set of booleans, that is, the set which just has two elements, true and false. And the thing is, in set theory, if we want to talk about a subset, for example, this subset E of D here, well, we can say that that kind of corresponds with this kind of so-called indicator function, chi of E. Now, this sends the elements of E to true and the elements outside of E to false. And in such a way, this function corresponds to this subset here. Now, there's a sort of object or space in our world of smooth spaces, which is also called omega, which has a similar sort of property. And that means that if we take And that's extremely interesting, because basically if we have a space S, then we can think of a part of S as corresponding to a sort of arrow from S to omega. And in fact, if we write omega to the power of S, then that actually is sort of like the space of sub and another thing that's really interesting is that if we think about omega to the power of S, well, we can actually think of this as the kind of space of parts of S. And so, for example, we might want to consider a path P on omega to the power of S, and you could think of that as a sort of way that some substructure of S might change over time. So, for example, you could maybe model the growth of a flower as some kind of a subset of 3D space which is changing over time, and you could probably define vector fields and so on to govern how shapes might evolve over time. Another thing I want to briefly mention is the idea of being able to stick spaces together. So we've already encountered this idea of less than. So the notion that x might be less than y when x and y are points on our smooth line. Now we also have another symbol which is greater than or equal to, and we define that to say that x is greater than or equal to y if and only if it's not true that x is less than y. And so we can use the kind of usual notation for the unit interval as being the part of the line consisting of all of the values which are greater than or equal to 0 and less than or equal to 1. And now let's talk about how we can make a smooth space which looks like a circle in a sort of way which a topologist would like. And basically that idea is to get this unit interval here and glue the endpoints together, thus making a loop. Well, actually, it doesn't make a unit circle, it makes a loop, okay? Something that's topologically equivalent to a unit circle. So basically, the way that we can do this is that if we have these two maps, f and g, from 1 to our unit interval, well, what we can basically do is take the sort of what they call the co-equalizer of these two maps. Basically what that means is that we can form a sort of equivalence relation on B, and we really want to pick the minimum equivalence relation on B, which is such that f of x is equivalent to g of x for every x in B. And then if we just identify each pair of points which are equivalent under this, then that gives us this space C. So this is pretty similar to how co-equalizers work in sets, if you know about that kind of thing. Another thing I want to come back to briefly is the idea of maps. Okay, so we've thought quite a bit about this idea of what a map f from R to R is, and it's interesting that there are several different ways of visualizing this kind of thing. So for example, we can think of such a thing as corresponding to a point of this map space R to the power of R, or we could think of it as corresponding to a sort of graph. But I like this kind of idea because R to the power of R, we can really think of this in fact as an infinite dimensional space. So one interesting question is, we can ask, well, what's a path in this space of maps from R to R? And we can actually get at this. We can think of it a couple of ways actually. One is that if we have a map from R to R, we can just draw that as a graph. And then the thing is that we can just imagine that kind of graph changing over time, sort of like a string deforming. And we can see that this corresponds with our intuition in a nice way, because what happens if you have a load of curves and they're deforming? Well, you can visualize that as a surface just by stacking each of those curves next to each other. And we can see that this agrees with the kind of ideas of synthetic differential geometry, because by the way that we can make arrows correspond with each other using exponential objects, we can rewrite this kind of arrow or map as an arrow like this, from R times R to R, and that's a surface. And so a final thing I wanted to say is a remarkable property of this R to the power of R here, and that's essentially that in a sense it sort of corresponds to infinite dimensional space. So in particular, let's suppose that we had some kind of shape in n-dimensional space, and I want to show that we can embed this in R to the power of R. Basically, I want to show that this space is, in a sense, big enough to hold any structure. So let's consider some kind of a part of n-dimensional space. So we call that S. Now, there'll be a corresponding kind of function from n-dimensional space to our truth value object, omega, which is basically classifying this kind of part. In other words, this is a function which is just sending the points of n-dimensional space which are present in S to true. Okay, so it's like an indicator function indicating which points are actually in our subspace. Now, let's say we want to model and so we could think of this S here as a sort of general shape in n-dimensional space. And we could actually then embed that shape in this space r to the power of r. And basically, we can form this kind of part of our function space, which would look like S. So this consists of all of the functions f from r to the power of r, which have these kind of power series involving these coefficients b1 and b2 all the way up to bn, which is such that these coefficient values b1 all the way up to bn basically correspond to points of this space S, which we're trying to model. So you can see from this kind of idea that r to the power of r is an extremely rich sort of space. And sometimes I wonder if it might have there might be some kind of cosmic relevance to this sort of space, because it seems rich enough to capture so much geometry and also so fundamental with respect to the ideas of the way we think about numbers and so on.